Hello, test, test. Looks good. Hello, everyone. Thank you for coming to the first. Oh, can you point the camera at me? Sure. Thank you. Thank you for coming to the first undergraduate colloquium of the year. Edgar, PhySU VP Edgar, has generously agreed to give a presentation on density functional theory. And please, after the talk, feel free to have some fruit if you would like. So if you want to ask a question, just put your hand up and I'll come and I'll give the microphone, okay? Just so you folks online can hear you. Let's all settle in and give a big round of applause to Edgar. Thank you very much.
Yeah. Thanks, Marty, for the introduction. I'm honored to be the first presenter this year of the PhySU Undergrad Colloquium, which has been a long-standing tradition since the start of this year. Yeah. So today my talk is going to be about it's going to be an introduction to density functional theory. So density functional theory is like this quantum mechanical simulation method, which is used a lot in solid state physics and in computational chemistry. And it has a variety of applications. So I'll talk a bit about the theory behind density functional theory today. And for the second half of the lecture, if we have time, I'll talk about a bit of my work this past summer. So this past summer, I was working at the Computational Science Initiative at Brookhaven National Laboratory in the US. And I worked on a DFT-based project there. So if we have time, I'll talk a bit about the DFT portion of that. Yeah, so what exactly is density functional theory? So essentially, density functional theory is a quantum mechanical like simulation method that's used a lot in chemistry and solid state physics. There's a lot of uses for it. For example, one thing it's used frequently is to compute band structures of different materials. So here I have I guess the cursor doesn't show up, but I have a like plot of a DFT computed band structure of silicon. And the figure on the left is an example of a molecular orbital computed using DFT. Yeah, I'll go into a bit about like the motivation behind why DFT is used as like a computational method for chemistry, and a bit behind like how like the theory behind DFT, like how it actually works. Um, yeah, so to start off, let's talk a bit about the quantum mechanics of chemical systems. So how many of you guys have like a background in quantum mechanics or some background in quantum mechanics? Okay, it's 2/3 of the room. That's pretty good. So, if you have like if you've done quantum mechanics before, I'm sure you've seen this equation, the time-independent Schrodinger equation, which is kind of this alongside the time-dependent Schrodinger equation are like the Newton's laws of quantum mechanics. So the time-independent Schrodinger equation essentially tells you like what like the solutions to the time-independent Schrodinger equation essentially tell you like what are the allowed energy states of the system. And when you solve for this, you can do a lot of things. Like you can figure out like for example, you can compute like the dynamics of the system, how it'll evolve over time, so on and so on. And so the solution of this like equation is called the wave function. And so yeah, to find like how exactly a system will behave, a quantum system will like behave and evolve over time, you kind of just have to solve for this equation. I mean, it looks pretty nice right now. So how bad could it be if we apply it to chemistry, right? Unfortunately, it's pretty bad. So as you can see here, this is the full like Hamiltonian for say any like chemical system. If you have like n atomic nuclei and n electrons, so like big N for like the atomic nuclei and small n for like how many electrons there are. So this is like the full Hamiltonian, the full like Schrodinger equation. And we still have the kinetic energy and the potential components. which I've labeled in the slides. But when you like fully write them out, you can see it's pretty bad. But I'll quickly like explain what the individual terms mean. Most of it should be fairly like understandable if you've done like electrostatics or like basically like, basic electrodynamics before. But it's just a lot of like terms, so it gets pretty messy. So I mean, the first part is just the kinetic energy component. So you have the kinetic energy of this one would be like the kinetic energy of the electrons, and this corresponds to the kinetic energy of the atomic nuclei. And then here you have the potential part of the Schrodinger equation. So here you have this term essentially corresponds to the electrostatic like attraction between the electrons and the nuclei. So you sum over like all pairs of electrons and nuclei, and you multiply by the charge, and you divide by like the distance between the like the electron and the nuclei. That's how that's basically the Coulomb potential between like the nuclei and electrons. So here these terms are also similar. This would correspond to the electrostatic repulsion between electrons, and this term corresponds to like the electrostatic repulsion between the atomic nuclei. So yeah, this system is clearly like it's there's as far as like we know, there's no analytical solution to it. So if we want to actually make this equation like useful and actually be able to predict things like chemistry, we have to like simplify it quite a bit. So we have to find a better way to solve this system. So the first thing we can do is to make what's called the Born-Oppenheimer approximation. So essentially what the Born-Oppenheimer approximation is it's the assumption that you can treat the electronic and nuclear degrees of freedom separately. So essentially like the nuclei are much heavier than the electrons. So you can kind of like, so they kind of operate on different like time and on different like time scales and like mass scales. So as a result, you can kind of just fix the atomic nuclei and treat them as classical point particles, giving off some like Coulombic charge. And then the electrons behave quantum mechanically within this like classical potential. So when you make this approximation, this reduces the problem to solving for just what's called the electronic wave function. So here I have the Hamiltonian for what you like reduce the like molecular Hamiltonian to when you make the Born-Oppenheimer approximation. So you can see all the terms that correspond to nuclear motion and the like attraction or like repulsion between the nuclei. Those are all gone. So all you have left is just the kinetic energy of the electrons, the attraction between, this should be, oh yeah, this isn't nice. The sign is correct. So the attraction between the electrons and the nuclei, and the electrostatic like repulsion between the electrons. And so this is essentially the electronic Schrodinger equation. So before I go into how we use DFT to essentially solve for this electronic Schrodinger equation, I'll talk a bit about the variational principle of quantum mechanics. So the variational principle is it's a method for solving quantum systems when we in the case like if we have like say a guess for what the wave function might look like. So because even here you can't exactly solve for this like this equation analytically. You still have to you still can't like really solve for analytically, mainly because of the electron interactions. So the interactions encapsulated in that last term. So essentially what the variational principle is suppose suppose you want to find the ground state of a quantum system. So you want to find the lowest energy state of a quantum system. It turns out that you can, if you take any arbitrary like quantum state that's allowed by like this Hamiltonian, and you compute its expectation value for the energy, it'll always be higher than the expectation value energy of the ground state, so the ground state energy. And I won't go into I won't go into the exact proof behind this just for the sake of time, but it's not too bad if you if you've done linear algebra before. But essentially, you want to what this principle tells you is that you want to find a wave function that minimizes the expectation value of energy, and then if you can find such a wave function, this wave function will be likely a good approximation of the actual ground state wave function. Um, so just to make this idea a bit more concrete, since I know like the variational principle isn't taught until maybe fourth year quantum mechanics, 456, I think. So I'll just give an example of how you would actually use this principle. So suppose you have like this linear potential here, and you want to solve for like the Schrodinger equation for this like linear potential. So what you can do is you can take this Gaussian you can suppose the wave function takes the form of like a Gaussian. So this let me draw it out actually. Maybe it'll make more sense. This potential kind of just looks like a V here, and um, just like from what we know about quantum mechanics, like you'd expect like if the for the ground state it's going to have some energy like maybe up to here, and you would know that like outside of this energy it would decay exponentially, and then here in this it would like have a maximum in the center of the well, and then it would kind of like have a peak like this and then go to zero outside. So you would guess like maybe a Gaussian is a good approximation to what the actual wave function would look like, the ground state wave function. So here what we can do is we can take like a trial Gaussian wave function, a e to the minus bx squared, and we want to find the value of b that minimizes the what's what's it called, the like ground state energy or the expectation value of energy. So essentially we can just like take these, we can evaluate these integrals. I'm not going to do the full computation out, but essentially what you would be doing is you would take like e to the minus bx squared, and then you have a, which is like a normalization factor, minus h bar squared over 2m nabla squared plus alpha x. So you would just be evaluating this integral, and then you also have the, let me rewrite this. And then you also have this part in the denominator, which is essentially just to normalize the wave function. Since if you guess like an arbitrary wave function here, it might not be normalized, like the a times e to the minus bx squared. So you want to keep it, and if it's not normalized, then you could have like a higher energy or a lower energy than like what the actual normalized quantum state would be. So that's why you have this like thing at the bottom. So if you evaluate this like interval, and this is the expectation value of energy, that you'll essentially get like what I have in this slide there, h bar squared b over 2m plus yada yada. So now to find the value of b that minimizes this expectation value, you can just take, like, from first year calculus, you can just take the derivative of this expression with respect to b and then set it equal to 0 and solve. And then you'll find that b naught is am it's that expression right there. So yeah, this is an example of the variational principle in action. And so I wanted to cover this because density functional theory, like the idea behind it essentially is the variational principle. So here, in the previous example, the toy example I just covered, of like using a Gaussian wave function for this, a Gaussian like variational wave function for this linear potential. Um, you're varying like the wave function and trying to find an energy that minimizes the an energy, or sorry, a wave function that minimizes the energy. But the idea behind DFT, actually, density functional theory, is to instead suppose we can take the electron density of like some chemical system, and we can write the energy as a functional of the electron density. In that case, the variational problem becomes what's the electron density that minimizes the oh, should I be concerned about that? Or the Zoom workspace? Okay. Okay. Let me close it and see. Okay. Is it still running on the oh, I think so. Oh, it must have Zoom crashed, I think. Just share your screen. Okay, okay. But I think I need to rejoin. Yeah. Okay. Um, Let me like move this out of the way. All right, nice. So yeah, so as I was saying, so basically the idea behind DFT is to reformulate the variational problem for quantum mechanics in terms of the electron density instead of the electron wave function. And so to make this like a bit more rigorous, so um, like so this expression here kind of just expresses like the fact that energy can be written as like a functional of the electron density. And really what this means is that you need to have a what this means is that if you take some electron density, you can take a functional that takes this electron density and I guess let me just explain what a functional is. Essentially, it's just a function of a function. So like in math, normally like functions you take like numbers to numbers, but a functional is essentially something that takes a function and maps it to like either a number or some other function. So here, the idea behind DFT is that there's a functional that takes the ground state density or the electron density of some chemical system and maps it to the energy of a system. And to make this like a bit more rigorous, like how do we know like there actually exists such a functional? There's these two theorems which were developed, I think, or like formulated, I think, sometime in the 1950s or 1960s, called the Hohenberg-Kohn theorems, and they essentially let us put like DFT on a more rigorous like mathematical footing. Oh, my keyboard isn't. Okay, there we go. So essentially, what the Hohenberg-Kohn theorems are, the first Hohenberg-Kohn theorem tells us that uh, the external potential. So here the external potential for a chemical system is essentially like in the Born-Oppenheimer approximation, it's the potential from the atomic nuclei. So the first Hohenberg-Kohn theorem tells us that the external potential is a unique functional of the electron density. So what this means is that if you have two potentials like v of x and v prime of x, and they differ by more than a constant, let's suppose like you solve for these, like the Schrodinger equation for these systems, and you solve for like the ground state wave functions of these systems. Then when you take like the ground state wave function, you can also compute the ground state density, because that's just taking the amplitude squared of the wave function. The first Hohenberg-Kohn theorem tells us that these ground state densities are distinct. So a corollary of this theorem is that the ground state wave function is a unique functional of the energy. So what this means here is that this expression is valid. So the right-hand side of this expression is valid in that I'm writing like the ground state wave function as a functional of the electron density, right? And so that so that's the first Hohenberg-Kohn theorem. So the second Hohenberg-Kohn theorem tells us that the electron density that minimizes the energy functional is actually the ground state density of the system. And this is really just the variational theorem like reformulated for the electron density. So now that we know that instead of for like say some chemical system, if we want to find the like ground state, if we want to find like say the ground state energy of the system and like the ground state observables of the system, so like the energy or any other observable, you can simply rewrite them as functionals of the ground state density. But then now there's the actual problem of how do we solve for the ground state density. And so this is what so these two theoretical chemists, Walter Kohn, who's the same Kohn as the Hohenberg-Kohn theorems, and Sham, they developed something called the Kohn-Sham equations, which actually let us solve for the ground state density via like under like the the premise of the Hohenberg-Kohn theorems. So the idea is that the interacting n electron problem. So essentially here the electronic like Schrodinger equation I have here. This is still kind of hard to solve because, as I mentioned, we have the interactions between the electrons, right? The last term on the left-hand side, the 1 over Rij. That makes the system still like difficult to solve. So the idea here for the Kohn-Sham equations is that you can take this interacting electron problem and map it to some non-interacting electron problem that gives you the same ground state density. And I won't discuss like the exact like mathematical proof behind like there actually exists such a non-interacting electron problem and such, but it exists, and under like certain like I guess mathematical like hypotheses, but it exists, and you can find like you can do this like mapping of these problems. So what ends up happening is that so first of all, when you solve actually let me go to the next slide. Or so when you like when you do this mapping, you actually get what's called the Kohn-Sham equation, which is on the it's the second equation on this slide. And the solutions to these equations are basically the solutions to the non-interacting electron problem that will give you the same ground state density, the like correct ground state density. And the idea behind like how to derive this equation is you first write the energy functional, so the energy as a function of the ground state density. You rewrite it in terms of these orbitals. So you do so the first term in this like energy functional on the bottom, that corresponds to the Kohn-Sham kinetic energy. So this is kind of, in a sense, the kinetic energy of these like fictitious non-interacting electrons. The second term is called the Hartree term, and that's essentially that essentially corresponds to like the classical electron-electron repulsion between like these uh, non-interacting electrons. But really, like in like the Kohn-Sham formulation, this like electron-electron repulsion is treated as like some mean field that's produced by all the electrons collectively. So in a sense, like it's kind of independent of the electrons, but it's still like not really. But I guess when I explain like how the Kohn-Sham equations are actually solved, I'll like um, it'll make a bit more sense. The third term is the external potential, so that's just the potential as a result of the atomic nuclei. And the last term is called the exchange correlation functional. And this is actually probably the most important part of DFT, because this term essentially is the correction term for all of these. So this essentially you take all of the errors that would be induced by like just treating this as the total energy, and you would like take like you would like subtract that from like the actual ground state energy of the system, and the remainder is called the exchange correlation functional. And the reason why there's still like DFT is still like not a fully like it's still pretty approximate like in terms of the actual computations that are carried out, is because of the fact that this exchange correlation functional, no one knows what it actually looks like, if there's like an analytic formulation for it, and the best people can do is just come up with like approximations for it. So yeah, when you the idea behind like how you derive the Kohn-Sham equations, or the Kohn-Sham equation from this energy functional. If you've taken like physics 354 before and you've done like the Euler-Lagrange equations, it's a similar idea, because in the Euler-Lagrange equations, you're trying to minimize the action of a system, and you take the action of a system is a functional of a particle's path or a particle's like trajectory, and you do like what's called affecting a variation on that path. So you use variational calculus, and through that you derive the Euler-Lagrange equations, and that gets you the actual path the particle takes through space. And so it's a similar idea here. You use variational calculus on this like energy functional, and that gives you the Kohn-Sham equation. And so essentially all the terms aside from the kinetic energy term, when you affect the variation on all of these terms, they go into this effective potential term. And this effective potential term just looks like this. So it's a sum of the so basically it's a sum of the like external potential from the atomic nuclei with the like mean field from all the electrons, and the exchange correlation functional, or the functional derivative of the exchange correlation functional. So now what's left is for doing DFT is like how do you solve for the Kohn-Sham equation? And the actual like method that's used in practice is called the like self-consistent field method. So if you notice in this Kohn-Sham equation, the effective potential actually depends on the ground state density itself, right? Because first of all, the electron repulsion term that depends on the ground state like density, and in addition, the exchange correlation functional is also a functional of the like ground state density. So what this means is that actually, because the ground state density itself is just the sum of like all these Kohn-Sham orbitals, all the solutions to this Kohn-Sham equation, that means that this equation actually depends on its own solutions. And so there's no really nice way to just solve for an equation like that. So what you do, what's done in practice is you try to arrive at a self-consistent solution. So the way this is done is you first give an initial guess for the ground state density, and this will depend on what like the particular DFT package that you use, how they do this initial guess. Like but essentially you have an initial guess. This initial guess will go into the effective potential here. And now you actually have an equation that you could numerically solve, and you can solve for like the solutions of this system. So now when you solve for the Kohn-Sham equations for this, when you substitute like the electron density into this equation, you'll get a new electron density, right? Because obviously there's no reason why when you solve for this system, you should get the same density as the initial guess. So you solve for this density, and then you check if this new density has converged. So essentially, is it close enough to your original guess? And if it's not, then you basically repeat this process. Now you take this new density, you plug it into the effective potential, and you solve for the Kohn-Sham equations again. And you keep on doing this until you reach your convergence threshold. And this would be, if you actually do like DFT in practice, this is something that you would set yourself, what's an acceptable like condition for convergence. And so if it's converged, then you're basically done. You have the ground state density of the system and the ground state energy. So in practice, in principle, once you have this ground state density, you could also solve for first of all you can find the ground state wave function, and in principle you can also find all the excited states. We have a question. Yeah. Yeah. Mm-hmm. So no, so you don't plug in the first initial guess. Sorry, I guess this isn't very clear, but you don't plug in the first initial guess. After you solve for the density, right? The Kohn-Sham equations, right? You can find a new density from the orbitals that you in your solution, right? Because you can just take the amplitude squared of the orbitals and then sum them up, and then that gives you a new density. And then this new density goes into the Kohn-Sham equation again, and then you resolve for this equation with this new density plugged in. You keep going in this cycle until you reach convergence, and that's why it's called self-consistent field theory, because the field is like self-consistent with the electron density. Um, yeah, so yeah, so I guess where was I? So if you actually, so you see, I was talking about like how you can, in principle, it's possible to solve for all the excited states, but again, no one really knows how to actually solve for the excited states of the system. So what's actually done is you take these Kohn-Sham orbitals. So remember, like initially I introduced these Kohn-Sham orbitals as kind of like a fictitious system, right? It's just a convenient like mathematical trick we do to like make this problem actually solvable. But it turns out that like when like chemists and physicists, they actually use DFT, they actually take these Kohn-Sham orbitals to be real like actual like physical electron states for this system. And under what conditions this like approximation is allowed, it's it can like vary, like there are like conditions in which like this approximation is like good enough. But it does turn out that like if you have you can find like exchange correlation functionals that will give you like Kohn-Sham orbitals that match like experimental results. And this is like a whole field of like DFT research. So there's a lot of people just coming up with new like functionals all the time. And but yeah, I guess so in addition to that, The actual implementation of DFT actually depends on a lot of like technical details. So again, first of all, there's the choice of the exchange correlation functional that I mentioned. Again, no one knows like what it looks like, so people come up with like different approximations to what they think will like reasonably reproduce like experimental results. So of course, first of all there's ab initio methods, which kind of I guess you can say there is some theoretical justification to the form of these functionals for ab initio functionals, but again, they're also like approximations to what it would actually look like. There are semi-empirical functionals. So semi-empirical functionals uh, take like experimental data and try to fit the functional so that your DFT results match experimental data. And then there's also like hybrid functionals. So hybrid functionals are kind of like a mixture between like either ab initio or semi-empirical functionals and Hartree-Fock functionals. So Hartree-Fock is another computational chemical technique that is actually used a lot more before like the advent of Kohn-Sham DFT. But people also take functionals from Hartree-Fock, which operates in a kind of a similar manner, and they will like um, uh, they mix it with like the DFT functionals. There's also like say the choice of basis set in DFT. So if you've done like quantum mechanics before, you know that like any arbitrary quantum state can be expanded in terms of a basis, and then you can reduce a lot of like quantum mechanics to like like a linear algebra problem. So this is what's done in DFT as well. You pick like a suitable basis set. So there are different like bases you can choose. For example, an atomic basis set would basically be you take you expand like you expand like all your expressions out in terms of like atomic orbitals. So the hydrogen atom orbitals that you've done in 256 or 356, or if you're in 151, you'll cover, or if you're in 151, you'll cover like this in 152, I think. Another choice is a Gaussian basis set. So there you would take like your basis functions to be Gaussian functions. And finally, you also have plane waves that can be used as a basis set. So plane waves are essentially like, for example, light is a plane wave. It's something that the phase and the amplitude of the wave is like constant within the plane. And because plane waves describe a lot of like solid state physics, plane wave basis sets are actually used in a lot of like solid state systems when you do DFT. And then there's also another a technical like detail that's considered when doing DFT computations is the choice of pseudopotentials. So pseudopotential, so essentially when you have like I guess I can like draw it. So like when I mentioned the external potential before in the energy functional, I introduced it as like just the potential arising from the atomic nuclei, but there's no reason why it has to be like some Coulombic potential arising from like the atomic nuclei. It could be like any arbitrary potential. So like what's done in a lot of DFT computations is you basically you treat like so instead of like a like what's it called? Instead of a like Coulombic potential like this, you'll kind of have yeah, instead of like a Coulombic potential like that, or I guess since it's attractive, it looks more like looks more like this. But instead of something like this, you'll like replace it with a potential that accounts for like the core electrons. So you kind of like take the core electrons and you treat them as like something that's not really like what you're solving for in this like quantum mechanical system. You just treat them as like some charge distribution, and you treat them as some like charge distribution, and they give off some like electrostatic potential as well. And then you can solve for DFT, solve for like the Kohn-Sham equations under this like new potential. So this is done a lot in conjunction with plane wave bases, because it turns out that when you use like plane wave bases, um, near like atomic nuclei, you'll have like very bad convergence. So yeah, I guess if you're interested in like learning how to do DFT, because this is actually, I mean, compared to a lot of like experimental physics, which obviously you need um, like expensive lab equipment to do, which you most likely won't have access to. DFT is something you could just do like on your own computer and you could learn on your own. And so I want to give like some like examples of resources you can use to learn DFT on your own. So first of all, first thing is like what DFT package you use. There's a lot of DFT codes out there, but a few popular ones are VASP, which stands for Vienna Ab Initio Simulation Package. Another one is Gaussian. And then the third one, which is like my personal favorite, because this is the one I use for my summer research, is Quantum Espresso. And so the first two actually require licenses to use. I believe they both require academic licenses, which might make it harder for you to get like acquire them. But Quantum Espresso is actually like open source, and you can, if you have like say Linux, you could install it and like run it on Linux on your own. And then like some resources like that I use for learning DFT on my own. So this first like video, this first like YouTube playlist here is on it's a like lecture series by a chemistry prof at I forgot which university, but his name's Chris Kramer, and he has a whole series on computational chemistry, and this playlist is his like lecture series on like the theory and history behind DFT. So this was pretty useful for me for learning how like the theory actually worked. Another thing is this playlist here for it's a tutorial on how to use BRI. So BRI is like this GUI for Quantum Espresso. Um, and if you're like just starting out, and especially if you're like unfamiliar with Linux, I think it's a good starting point to use. It's pretty like intuitive. You can kind of just take like the geometry files for like whatever atoms you're looking at, and just open them in BRI, and you can like it has like a nice graphical interface. And then this last video series is like a video series on like how like tutorials for Quantum Espresso, and he covers like how to run like the different modules in Quantum Espresso on Linux and stuff. Yeah, if you want to take a picture of the QR codes, and if you want to like look these up yourself later, feel free. Yeah, so that I don't think we'll have time to play these playlists. Oh, screen sharing has stopped. Let me.
You're good.
Oh, I'm good. Oh, it's 5:53. Okay. Yeah. Okay. I guess. Yeah, it's okay. I guess I won't really have time to cover like the research I did over the summer. But I can start taking questions now. If anyone has any questions about the talk?
Yes, yes. Okay, any questions?
What's my favorite functional? The BLYP one. That's the one I use for like my work over the summer. It's like the default one on Quantum Espresso. Favorite basis set? Plane wave basis set. You're a DFT enjoyer? Oh, nice. Any other? Siobhan? Mm-hmm.
Hey, thank you for the presentation. So, okay, I guess you can't share your screen anymore, but I have a question about the self-consistent equation slide. So you said that you kind of plug in your guess for the density into the Kohn-Sham equations again.
Mm-hmm.
How do you know that each iteration will be closer to convergence than the last? How do you know it's
There's
not
no
going to just...
guarantee, actually. Yeah, that's a good question. There's no guarantee that that like each iteration you'll actually like get closer and closer to like a convergent solution. So I mean, this is a problem like chemists, like computational chemists or like physicists, they'll face when doing DFT computations. They'll run they'll run the calculation for like hours, and then at the end it's like not converged. But there are like different tricks that like DFT codes will do to try to achieve convergence. So one thing is called mixing. So essentially what mixing is, it's just, it takes, instead of taking the new ground state wave function and plugging it into the potential, they take you take like a mixture of the first ground state wave function and then the new ground state wave function. So it's, you could do, I think it's like some linear combination of them, and you plug that into the Kohn-Sham equation instead. So obviously, because like this will change like the because you're not changing the like potential as much, since it's incorporating some of the previous ground state density. This makes convergence like easier. Another thing that is done is called thermal smearing. So again, like when you solve for the Kohn-Sham equations, you get like a set of orbitals, right? And you can get like arbitrarily many orbitals as you want, because you know you can have like as many like say like a part, like for example in the particle in the box quantum problem, you have like an infinite number of solutions. So it's the same with the Kohn-Sham equations. There's an infinite number of solutions, but then the ground state density itself depends on which solutions are actually occupied by particles. So you take the occupied particles and then use those in the ground state solution in the new ground state density. But what thermal smearing does is, so first of all, if you say have like in the zero temperature limit, the particles are just occupied, like it's like a Heaviside step function, right? You just occupy the particles up until the Fermi energy. So that would be like at 0 Kelvin. Thermal smearing, you occupy the orbitals by a Fermi Dirac function, and then you use that to compute the ground state density instead of like the like zero temperature ground state like occupancy, and that helps with convergence, because it turns out if you just use a Heaviside step function to compute like if you just use a Heaviside step function, right? Sometimes like the topmost orbital will like sometimes completely change, um or like say like disappear at each iteration of the self-consistent calculation. And then when it like say like not disappear, sorry, but it'll go from being occupied to unoccupied, like just on and off like that, which that'll affect the convergence a lot. So when you introduce thermal smearing, you'll occupy these states fractionally. So instead of the uppermost state being like completely going from like occupied to unoccupied, there's some fractional occupancy on it that makes it so that like this change between like each iteration isn't as much. Yeah.
Thank you so much.
Does anyone have any other questions? Ivan?
I have like a really basic question. So when you rewrite your wave functions in terms of, you write these functionals in terms of the density functions, right? So I like that's the whole point. So that sounds like you're just changing like from position basis into some kind of density basis or something, right? Is that kind of the idea behind it? And if so, like big picture, what is the advantage of doing this kind of basis change from like just writing a general wave function instead of writing it as a functional of a density function?
That's a good question. I'm not sure if it's exactly think of it as a change of basis, but from what I know, I mean, the advantage of this over doing like say just computing for the wave function. Well, before DFT, the main method used in computational chemistry, the main is called Hartree-Fock theory. And Hartree-Fock theory actually, you actually try to find the electronic wave function of the system, and that's done by assuming that the electronic wave function takes the form of a Slater determinant. I'm not sure how familiar people are with like Slater determinants, but basically, if you have, the idea is electrons are fermions, and so the wave function that describes electrons, it has to be antisymmetric. So if you take like psi of x, or say you have two particles, psi of x1 and psi of x2, and so that this like coordinate describes particle 1, and this coordinate describes particle 2, and if you switch like the positions of the particles, right, this actually has to be like negative of that, right? This is anti-symmetry. And so if you're trying to solve for like an electronic wave function, you're kind of trying to solve for all. What Hartree-Fock does is it tries to solve for the individual orbitals of the electrons, right? The individual like allowed states of the electrons. But because the electrons are fermions, this electron wave function has to be antisymmetric. And so a Slater determinant is something that anti-symmetrizes the electronic wave function. So if your electron orbitals are like 5,1, 5,2, so on and so on, 5n, you take the determinant of these wave functions. So you write out like phi2, phi-n, phi1, phi2, phi-n, phi1, phi2, phi-n, 1 over. So that this is a Slater determinant, and so Hartree-Fock assumes that like you can. Hartree-Fock basically tries to assumes that the electronic wave function takes the form of a Slater determinant, and then it tries to find the orbitals that minimize the this Slater determinant energy under like the variational principle. But the reason why DFT is a lot more popular now over Hartree-Fock is because I'm not sure exactly like the details behind it, but DFT like goes something like I think n to the 4 in terms of the size of your basis set, because when you expand things out in terms of the basis, you actually have to pick like a finite like cutoff point for where the basis ends. And so Hartree-Fock goes something like n to the 4, but DFT goes something like n to the 3. So it's just computationally, it's like faster. And it also turns out that DFT is able to reproduce like some interactions that Hartree-Fock isn't able to. Because again, like I talked about with the exchange correlation functional, you can kind of make it whatever you want. And as a result, people who actually do research in DFT, they try to come up with new like exchange correlation functionals all the time to like try to get it to fit experimental data, or try to get it to explain like some physical thing or account for some like physical like interaction. Yeah. Does anyone have any questions?
Okay.
Yeah.
Another big round of applause. Thank you everyone for coming. Again, we have some fruit if you would like, and we'll have another talk next week in this room at 5 p.m. Vivek is giving a presentation. I don't happen to remember the title off the top of my head right now, but it's on the. We'll make an announcement tomorrow. So, thank you everybody for coming.
So